what's being illustrated here, all of this ionic movement, the sodium potassium pump, and then the final value, negative 70 millivolts. As far as thinking about the magnitude of those forces, the resting membrane potential ends up being closer to the equilibrium potential for potassium. So if you think about the change of the membrane potential here on this line, all right. Okay, let's see, a question popped up here. Why are the millivolts positive? Okay, so this is a really good question. So when we think about the overall combined force, we're really looking at the magnitude of that force. All right, and so when we think about a positive millivolts, that's going to mean that the inside of the cell is becoming more positive. Remember that we said, and when we speak about the membrane potential value, that positive or negative really is just determining what the inside of the cell looks like. So if we think about potassium's equilibrium potential, it's negative 94 millivolts. That means that when potassium is at equilibrium, that means both of its forces are balancing out. And let's say we put a voltmeter into the cell at that very time, what we would read is negative 94 millivolts. So potassium stops moving when the cell is at a membrane potential of negative 94 millivolts. The equilibrium potential for sodium is positive 60. And so that means that when sodium stops moving, the inside of the cell is no longer extremely negative. It's very positive. Positive 60 in terms of the magnitude of that. So basically, our ions are going to try to move to get to equilibrium, and they're going to be moving, and the distance, the degree with which they are away from their equilibrium potential determines how strong the force of their movement is. Okay, I hope that makes sense. So if we look at this example here, here's the resting membrane potential, negative 70 millivolts. Here's potassium, sodium's equilibrium potential. So this is why sodium really wants to get into the cell, because when the cell is at rest, it's really far away from its equilibrium potential. And so it wants to rush into the cell until the membrane potential gets to positive 60, and then sodium will stop moving. All right. And so that 130 is the magnitude with which sodium wants to move to arrive at this equilibrium state or equilibrium potential. And so if the cell is at negative 70 at rest, we're going to have to rush enough sodium to overcome that negative 70, which again, the difference there is 70 to get to 0, and then add 60 to get to positive 60. So when we combine those two values, those two magnitudes, it's a combined force of 130 volts. And 130 being the change, right? And positive being the direction of that change. I hope that makes a little bit more sense. If we alternatively look at potassium, potassium's equilibrium potential is fairly close to the resting membrane potential, but it is still slightly more negative, which means that potassium is going to be moving in the opposite direction to get to its comfort zone, to get to its equilibrium value. So as the resting membrane potential is negative 70, potassium is going to trickle out of the cell. And again, the trickling is a representation of how far it is, or how far away it is from its equilibrium potential. So it's not very far. So it's not going to be a strong force. It's going to be a weak force, again, because it's fairly close. And it's going to be in the opposite direction, moving that positive charge out of the cell so that the inside becomes more negative, and that'll get us from negative 70 down to negative 94. All right. So as we think about the equilibrium potentials for our ions, and we think about the resting membrane potential, the resting membrane potential tells us how far these ions are from where they are comfortable, where they are no longer moving. And so that will be the magnitude of the driving force acting on the ions to try to get them to equilibrium. So another great question here, any resources, videos, worksheets to help us visualize and understand this concept. So yes, there is a video I'm going to link at the end of this. I think it's in this PowerPoint slide, and I've also shared it in Brightspace. And I think it does a really good job at just showing a graphical representation of these ions actually moving and the establishment of the resting membrane potential. So I'm going to link that in a couple slides coming up, and then it's also on Brightspace. So please have a look at that and go over this several times, right? This is not going to click right away. This is something you're going to have to work with a little bit, and then just practice that drawing that we did earlier, and you know, think about specific questions that you have, and I can kind of help work us through that as well. Okay, so let's keep going here. So we're going to just basically describe everything that I've just said in a few different ways, just to see if we can break it down a little bit further. So if the membrane potential is not at equilibrium for an ion, which is what we basically described, and we know that it's not, the membrane potential -70 at rest, and so it's not going to be at equilibrium for any of our two ions. Therefore, both of our ions are going to want to move. The strength, the force, the direction with which they want to move is all dependent upon the equilibrium potential and how far that away that is from that -70 at which the cell currently is. So the electrochemical force is not going to be zero if the membrane potential is not at the equilibrium value for the ion. And so the net force that acts on the ion is going to be moving it in the direction that is trying to get it to its equilibrium. Okay, so sodium equilibrium is +60. Therefore, sodium is going to want to rush into the cell, i.e. bring more positive charge into the cell to try to approach that +60 value. Okay, potassium's equilibrium potential is -94. Therefore, potassium is going to want to remove itself from the cell to get closer to its equilibrium, which is even more negative than the resting -70 value, right? It's -94. So the strength of the net force increases the further away the membrane potential is from the equilibrium potential of that specific ion. And remember, these equilibrium potential values are set, right? They are established values. They don't change. For potassium, it's always -94. For sodium, it's always +60. And so these ions, this is the value that these ions are trying to be at. This is where they're comfortable. This is where their ECDF is 0 and there's no longer any movement. So the further away they are from that value, the more the force they want to move. The closer they are to that value, the weaker the magnitude or force with which they want to move. All right. Okay. So just describing that here again further, the resting potential, -70 millivolts. The equilibrium potential for potassium, -94 millivolts. And I want you to think about this number as being where potassium is at home. Potassium is at home, it's comfortable, it is at a 0 ECDF. In other words, it's no longer moving, its forces are equally balanced out at -94 millivolts. Therefore, when the cell is at rest and the resting membrane potential is -70, it is 24 millivolts less negative than where potassium is at home. All right. Therefore, it's going to want to move to get to that value. And so it is going to move out of the cell. If you think about the two forces that are acting on it, the electrical force wants to move it into the cell. The chemical force wants to move it out of the cell. The chemical force is greater. All right. And so we subtract the difference there, and the magnitude. And when I say magnitude, it's the strength with which potassium wants to move is going to be 24, right? Which is relatively small or weak. And so the net force acting on potassium is weak, and it's going to be in the direction out of the cell. But since the permeability for potassium is very high, potassium is going to move out of the cell, but with that weaker force. All right. Okay, let's take sodium into account. So sodium is the opposite. Sodium has a equilibrium potential of +60 millivolts, which is way on the other end of the spectrum, right? First of all, it's positive, but also it's really a larger magnitude. Again, resting value is -70. And so when the cell is at rest, the membrane potential is 130 millivolts less negative than the equilibrium potential for sodium. So it's 130 millivolts away from where sodium is at home, where sodium is comfortable. If we think about the forces that are acting on it now, and again, the forces are trying to get it back to equilibrium. That's why we want to think about the forces independently and then combine them together. So the electrical force bringing it into the cell, the chemical force bringing it into the cell. And so that is the magnitude with which sodium wants to move to get back to its equilibrium potential of positive 60. Okay, so the net force combining those two forces is a strong force for sodium moving into the cell, but it has fewer doors, right? Because there's a lesser or lower permeability to sodium. And so those two factors, those two different types of movements of sodium and potassium balancing each other out is what brings us to negative 70 at rest. Okay. And I want to emphasize here, this is a point that kind of often goes overlooked, is that the ions never really reach their equilibrium potential. They never actually get there. The force that is trying to move them to get to that membrane potential value, the cell never gets to positive 60 millivolts. In fact, when we talk about the action potential, the farthest positive that it does get is positive 30. And so the equilibrium potential is really sort of a goal, right? It's a force in terms of this is where potassium or sodium is trying to get. It never actually gets there, but the forces that are acting on it are trying to move it to approach that value. Okay. All right. So again, just reiterating this, we've got small sodium leaking at rest because it has a higher or stronger force, but a lower or weaker permeability. And then the potassium is the opposite. It has a lower or weaker force and then a higher permeability. All right. And then the sodium potassium pump is returning the ions. That's really important. It's going to return the ions as they leak in one direction, they get pumped in the opposite direction. And that's what keeps the steady state. That's what establishes no further net accumulation of particles on either side. And if you check any neuron at rest, it's always going to be negative 70 because these movements are being balanced out. Okay. So here is where we are in terms of the resting membrane potential value. It's negative 70 millivolts. Here is what an action potential looks like. So when we talk about the resting membrane potential, this is the baseline of a neuron or muscle cell. This is the baseline of where it is at when it's comfortable. And so this is the backdrop where we can now excite the cell. We can open up certain different channels. We can open up sodium channels, for example. And as sodium begins to move into the cell, we can change the membrane potential and we can begin to excite this cell. And the excitement of a resting neuron results in the generation of an action potential, and that has the great ability to do work. So the action potential is how we can allow neurons to send signals to one another by exciting them. Simply by changing the permeability, by opening up different channels, allowing these ions to move, and then that will manipulate the membrane potential and allow excitement of the resting neuron. Okay, so this is why it's so important to understand how we start off here at negative 70, because then you are better able to understand how we can move from negative 70 to positive 30 back down to negative 80 or so, and then eventually get back to rest. So thinking about what's happening in a resting cell is really important to understanding how we can now excite that cell and generate an action potential. All right. Now, I know this is a lot of information and it's a lot of complex information. And I know that this takes a bit of time to process, organize, think about. So I'm not going to go any further today because what we're going to move on to really requires us to, just organize and process what we did today and let that soak in a little bit. And then we'll pick up and build on that on Friday. So I want you to take this remaining time, let's do about 3 minutes or so, and I want you to write down, and I want you to write this somewhere in your notes, but also share it in the chat box as well. Think about one question that you still have lingering after today's discussion. What's one area of confusion? What's one question that you still have unanswered based upon what we've just discussed today? So think about that, write that in your notes somewhere. This is a really good question to reflect back on, and it's going to help you understand your own learning process as well. So think back to the question that you didn't understand, and then later on, you'll be able to reflect and maybe even answer that question on your own, but also share those questions with me so that I can better understand exactly what areas we're having difficulty with.